What's up, AP Psych? This is your last lecture in our biological basis unit. It is all about our other senses that I haven't talked about yet. So, vision, hearing got their own lecture, but this lecture will include taste, smell, our sense of balance, and our sense of movement. Oh, and our sense of touch and pain. So, in the end, I guess I was saying that we were going to learn seven. I guess we're kind of learning eight. But you can see what I mean. Here we go. We've got taste and smell as their own, and then our body sense of touch and pain, which I kind of group together, and then vestibular sense and kinesthesia sense. Okay, let's start off with the senses connected to our body, or also known as our somatic senses. I just learned this word, this phrase from College Board. In fact, so I'm going to slip it in here. It's new to me, but it's the concept of embodied cognition. And I think this is kind of a cool phrase. It's a theory that the body is an important part of learning and cognitive processes, not just the brain. So basically, that our body is constantly sending thoughts to our brain and what we sense and what we feel, but then at the same time, our emotions and our senses from our brain are kind of telling our body what to do. So, for example, our nervous system is constantly interacting with our thoughts and our feelings. So, we might see food and then become hungry, and that might generate a sense in our stomach. That's something we'll talk about later. Or perhaps um, if we are excited emotionally, then our nervous system, our sympathetic nervous system kicks into gear. So it's what we call a feedback loop between the two. So our emotions and feelings are constantly sending signals to our bodies, and our bodies are constantly sending signals that impact our emotions and our feelings. Kind of a cool concept. Embodied, get it? Body cognition. Okay, so with that in mind, our body sends us signals all the time on how to think and feel. And feel is our next sense, our sense of touch. We actually have four different distinct skin senses with different receptors. And you can see you don't need to memorize this, but this image kind of shows you the different types of neurons and nerve endings that convey either pressure, temperature, vibration, or pain. And within the temperature topic, the sensation of something being very, very hot or the sensation of something burning is actually cold and warm receptors being activated at the same time. Yeah, another who knew sort of moment. We're going to dive a little bit deeper into pain. We know that we need pain. We need our sense of pain because pain tells our body that something has gone wrong. Usually it's damaged the skin or other tissues, but it tells us when we need to take care of ourselves or when we need to be careful with ourselves so our body can heal. It's important to know that substance P is another neurotransmitter, and this is a neurotransmitter for pain. So it specifically sends a pain signal to our brain. That too, I think is just kind of interesting. Substance P. Our nervous system seems to have kind of the ability to decide when to send us these pain signals, or perhaps how much of these pain signals to send. And you might think to yourself, well, then how come when I get a paper cut, it hurts really, really bad? But then other times when I've fallen down and maybe broken a bone or had a more serious injury, I didn't feel it, at least not at first. Well, that's because of the gate control theory. And this is the theory that our spinal cord contains neurological gates that either block or allow pain to be sensed. So essentially, when we hurt ourselves, like shortly before the beginning of this school year, I stubbed my pinky toe really bad, really, really bad. And I was screaming. I was going, ow, 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 ow. And interestingly, it's been like a month and a half and it still hurts. But when I first heard it, hurt myself, my afferent nerve for pain down by my toes opened up a gate, if you will, in my spinal cord, in my CNS to allow a signal to get to my brain so I knew that I hurt myself. Then what was the first thing I did is I grabbed my pinky toe and I started rubbing it. Well, the idea with gate control theory is that there's other large nerve fibers near those pain fibers that shut off the pain, like almost like distracting it from it. So, gate control theory is the idea that you can distract yourself from your pain. Um, and the reason we think that you can distract your body from the pain is to either soothe ourselves and calm ourselves down, or to allow ourselves sometimes to not feel really severe pain at first, to get out of the way of danger or to go attend to something more immediate for survival purposes, and then feel the pain in kind of a delayed way, um, when it's appropriate to then react to it and then take care of ourselves. So, kind of an interesting theory, one that we might, I have a little YouTube video that we might flesh out a little bit more in class. Pain itself is a biopsychosocial experience, meaning we actually biologically, of course, are feeling pain. But then perhaps looking around us and seeing who's going to see us or not, that might impact how we react to it. And then how we evaluate the pain is going to play a factor as well. So let's talk about my toe. Let's talk about my sore toe. I hit it. That pain sensory input is relayed by the thalamus to both the somasensory cortex, where in the parietal lobe, where I will feel it. I'm going to make a judgment, a psychological judgment. How bad is it? Where is it? How intense is it? What's the nature of it? Did I break my toe, or just is my toe just sore? I'm also going to have pain senses sent to my limbic system, my emotional control center, where I'm going to feel that emotional motivational component, the desire to escape the area of danger, walk away from the thing that I kicked with my toe, and perhaps go to a place where I will be more comfortable and then can tend to myself. And then there's another psychological experience in my prefrontal cortex where I think about, what are the implications of this? How bad is this? Is this going to ruin my ability to go for my run this afternoon? What about if I was going to go do something fun later? How bad is my pinky toe hurting me? How sorry do I feel for myself? Is someone going to come check on me if no one else is home? Do I even bother to cry or scream? Or kind of think of it like when you're a little kid and when you see, or if you see a little kid fall and get hurt, sometimes you know that if you ignore it, I mean, if you ignore the kid's reaction to the pain, sometimes they just kind of whimper and then move on. But if you go up to them saying, oh no, are you okay? Then they might have a more emotional experience. So there's a biological component, a mental component, and a social component to experiencing pain. One final note on pain is the concept of phantom limb pain. This is when someone who has perhaps an amputation, I don't know that this would come up if someone was born without a limb, but if you've had an amputation, sometimes people who have a missing body part actually feel pain in that area that's not there anymore. Some theories are that this is due to either that it's due to cross wiring in the sensory cortex. So essentially what that means is either nearby brain areas take over the sensations of the missing limb. So perhaps instead of feeling the pain from, I don't know, missing pinky toe, that the sensations attached to the toe next to the pinky toe might kind of crosswire in the brain. And as pain sensations are related to that toe, it might create a pain sensation in the next toe. Or it could just be a I don't think I should have an apostrophe there. No, or it is, nope, that's the correct apostrophe. It's a misinterpretation of spontaneous CNS, central nervous system, brain and spine activity in the absence of normal sensory experiences. So the brain knows that toe, let's say if my toe had been amputated, that toe was there before. And so it's got these sensory neurons that continue to go up the leg into the spine, into the brain, where you should feel something in that pinky toe. And so it's going to send off a signal. And so even though that toe might not be there, it's potentially, I would still feel that pain. This is another video that we will probably watch, from someone who actually experiences it and then a doctor who was helping treat it. Our next body sense is the vestibular sense. And notice I capitalized the B. You do not need to spell it with a capital B. It's just a mnemonic device to help you remember that vestibular sense is your sense of balance. It's your sense of your body's position with respect to gravity. Are you wobbly and falling over? Are you laying down in bed? Are you upside down on some monkey bars? What is the position of your body? Transduction for this sense, meaning the signal from gravity that you're tipping a certain way, occur and to change then into a neural signal into your brain occurs on the cilia and the fluid of the semicircular canals. I talked about these when we learned about hearing, but then I said they have nothing to do with hearing. That is true. So imagine these like horseshoe shaped tubes above both of your ears or kind of built into your ears that have nothing to do with hearing. And what they do is they are lined with little hairs. And I'm going to see if I can put my cup in front of the camera. And here's my cup. It is upright. My cup of juice here is not touching, well, let's say it would be triggering cilia, basically saying you're upright. But then if I were to take my cup on the monkey bars with me or lay down in bed with me, that would be weird. It's going to trigger other cilia that says, okay, you are now lying down horizontal and so on. If you think about it, think of the last time you did this because you were acting like a kid or when you were little, you would spin round and round and round and go wee. And then what would happen is that fluid, your body would stop, that fluid's going round and round and round, and then you stop. Well, that fluid continues to go in a circle round and round and round. So that fluid in your semicircular canals is now tricking your body into thinking you're still swirling, even though your body has stopped. That cilia then sends a signal into the brain, which is perceived in the cerebellum, because we know the cerebellum is key to balance and movement in the body. The final body sense is kinesthesis, or our kinesthetic sense. This is awareness of how your body moves. Your body parts position and movement, in other words, with respect to each other, sometimes known as hand-eye coordination. We don't have to look at our body when it moves to know where it is. So if I am looking at the screen right now, but I want to touch my nose, I can do that because without even looking, my kinesthetic sense tells me how to move my finger to touch my nose. If I am waving at you, this is also the sense that prevents me from slapping myself in the face. Or if I want to hit myself in the face, I can. So I know where my body parts are in relation to my other body parts because of my kinesthetic sense. This is transduced or turned into a neural signal with, oops, I've got a typo here, with receptors in my joints, my bones, my tendons, and my muscles. And then those signals are ultimately sent to my parietal lobe because remember, parietal is position, pressure, pain, all of our body senses, except for balance, are perceived in the parietal lobe. Our final category of senses are chemical senses. These are senses based on substances or stimuli entering the body as opposed to an energy wave. So there's not a frequency like in hearing or vision, and it's nothing internal in our bodies. Well, it will become internal, but it's things like, okay, so like my grape juice, it smells like grape juice. You want to smell it? You want to smell it? It's really yummy. It's Welch's. And so I didn't actually taste it, but I almost have a little sensation of it on my tongue because the chemicals are coming off my juice into my nose and I am able to receive it and make a neural signal out of it. So, as I speak of taste, taste is formally known as gustation. And what will happen is that food dissolves or food molecules will dissolve in my saliva, which is detected by my taste buds. What is super interesting is all those bumps on your tongue are actually known as papillae. So those are the actual bumps, and then the taste buds are the receptor cells on the papillae. So the papillae are the bumps on your tongue and they contain the taste buds, and the buds have taste pores with receptor cells connected to afferent nerves. That's a mouthful, but basically the taste buds are the receptor sites on the papillae themselves. This sense will decrease with age. It actually breaks down, and that's why a lot of times people become more tolerant of spicy foods as they age compared to when you're a little kid. If you burn your tongue or you scrape your tongue, like sometimes we do when we have pizza a little too fast, those taste buds will regenerate approximately every 1 to 2 weeks. But as you age, they don't all regenerate. Couple quick fun facts about your taste buds. We have roughly 100 receptor cells on each pore, on each papillae. And then we also know that our expectation, our sense of vision is involved with taste. We'll get more on that in a I think we had that actually in our sensation lecture, how the idea of flavor is strongly influenced by sight as well. So our expectation of how something will taste and how something looks and things like that also influence taste. But on its core, taste is the food molecules entering your taste buds. In the brain, that afferent nerve then sends a message to the thalamus and then to the temporal lobe. It is also near the olfactory area, resulting in sensory interaction. That is a fancy way of saying both your sense of taste and smell are connected, which makes sense because when you're not feeling well or you're kind of stuffy, your food might not taste as good. Super tasters are people that have more papillae, therefore more taste buds on their tongues compared to others. So if we were to put food coloring, green or blue food coloring on your tongue and like kind of taking like a little sample space, you could actually count how many papillae you have in a certain region. And if you did the same thing on somebody else's tongue, you could compare. And someone with many more papillae would be considered a super taster, or you might be considered a medium taster or a non-taster if you have very few taste buds. If you are a super taster, you have a low threshold for taste, which means you have so many papillae, so many taste buds, that a very mild taste could taste really strong. So if you're really sensitive to spice or really sensitive to salt, it would not take very much for you to notice it. You can detect very small amounts of taste in something compared to someone who is not a super taster. Apparently, 1 in 4 people are super tasters, and that there is that it's genetic. There you go. So if you're from a family of super tasters, you have a low threshold for taste. It doesn't take much for you to feel a very strong taste. I was going to make that more complicated than I need to. We have, oh, my little face bubble's in the way. Let me move my little face bubble. We have 6 traditional tastes, actually 5 traditionals, and one is brand new. Sweet, sour, salty, and bitter are some very common ones. Sweet tends to indicate to us an energy source. So if we're thinking kind of evolutionarily speaking, we know that sugar in things like berries, things that are sweet, could be a source of energy. If we detect something sour, we know that that is potentially a toxic acid, and our first inclination might be to kind of draw back or go bleh, and then we might learn to like it. Salty, we might crave salt when we know that our body is low in sodium because sodium is essential to our body's functioning. Um, Bitter, ours is also a signal of potential poisonous food. So again, we tend to learn to like that. We don't naturally like that. Umami is a newer taste that is kind of a savory, brothy, or meaty foods. And that is a signal that if we crave that, that we are craving maybe protein that in our bodies, and it helps grow and repair tissues. And then the newest one is oleogustus, which is a fatty flavor. It's like super new, super, super new, like in the last couple of years. And it's not necessarily a good taste, not like butter makes things taste good kind of fat, but almost just like something spoiled with this food kind of fat. That's the best I got right now. It's very new. And then on to our sense of smell. This is also our last slide. Olfaction is our sense of smell. In a similar way to food, odor molecules dissolve in the mucous membrane in our epithelium. So like this diagram, I'm not going to point it out myself. I'm going to use this diagram. So odor molecules come up into our nose, and then when it's moist as it should be, um, and the odor molecules are captured on the epithelium. They should kind of dissolve and interact with the olfactory bulb. What this is the location of transduction by the olfactory receptor cells. You should start to notice a pattern with all of our senses. Something from the universe, like a chemical or an energy wave, comes into our body, our senses, and then is transduced, or is received by receptor cells at sensory afferent neurons, and it's transduced and then goes to the brain, typically with the thalamus, but not smell. It goes to the olfactory bulb, straight to the temporal lobe, skipping the thalamus. My understanding is that the olfactory bulb is almost considered part of the temporal lobe, so it doesn't need to go to the thalamus. But smell messages also go to the frontal lobe, amygdala, and hippocampus, which tells us that smells have a strong connection to memory and emotions. So obviously, we've all had an experience when you smell something that your frontal lobe might be activated to like figure out what that smell is. Is it good? Is it bad? Perhaps it generates an emotional reaction, and it definitely smells definitely can trigger memories. And then finally, our bodies give off pheromones. These are essentially hormones that can be subliminally detected through smell by other humans to signal things like fear, anger, or potentially attraction. All right, there you go. We have just wrapped up all of our 5 or 6 or 7 or 8 senses, depending on how you count it. And we have just wrapped up this unit. Nice job, everybody.